Professor Feferman, which quantifiers are logical?
Thank you. I'm looking for Sergey.
Talk slow.
I won't start without Sergey.
He does that.
As I understand that he went home. Here he is.
Well, it has a battery.
Okay. We have a backup. Sure. All right, so this is another one. Okay, so thank you. All right.
So, very pleased to be here. I met Sergey 25 years ago in Moscow at a meeting of the Logic Methodology Conference there. And Sergey and Elena were very, very helpful to us, wonderful guides, became great friends, and I already understood that he had started his remarkable career some years before that. It's great to see how far it has advanced. Now, at that time, I wore a tie which Sergey admired very much, and before we left, we gave it to him as a gift. And he's worn it from time to time over the years since we've seen him, but I think he needs a refreshment. So. The diagram on the I don't know what you would call it. It's from an electron microscope of mitochondria, which are the powerhouse of the cell.
Yeah. It will take me probably 20 minutes to type properly. I've got to listen to you talk and I'll type it.
Thank you. So I first gave this a version of this talk, as you see at the bottom, in Ljubljana back in August. So we're starting a little late. Yeah? So first of all, the concern here is the exact limits of logic. And in general, we'd say that logic, what we're after is to characterize the forms of reasoning that lead from true sentences, invariably to true sentences, no matter what the subject matter. And they're supposed to be analyzed according to their logical, as opposed to their surface grammatical structure. Not exactly what that means, but sentence parts are generated by certain operations on propositions and predicates. And the question, what is logic, then reduces to, in a certain way, to the question, which of those operations are to be considered logical? And that's to be explained both by saying how truth of compounds is determined by the truth of the parts, and by characterizing those forms of inference that preserve truth in some sort of complete way. Now, that's a problem which has been discussed by many people. There's an interesting survey in the Bulletin of Symbolic Logic by Gomez Torrente of 2002. It's mostly been pursued either by purely semantical approaches or purely inferential approaches. So the two kinds, on the semantical side, going back to Tarski many years, but in an article, a posthumous article of Tarski's, 1986, that actually goes back to the 30s. He proposed that the operations that are logical are those that are invariant under arbitrary permutations of the universe. Galen Schur generalized this in a little bit of a way by saying, well, operations that are invariant under isomorphisms of domains. And Van McGee characterized what you get in that way as being exactly the operations defined by formulas in what's called L infinity infinity. You're allowed arbitrarily long conjunctions, disjunctions, arbitrarily long quantifier instances. And I critiqued that approach in a couple of articles in a more expansive way in 2010 in the Notre Dame Journal of Formal Logic. One of the reasons for the critique is it seemed to me evident that this goes far beyond what we would consider to be logic in the ordinary sense of the word. It really assimilates logic to mathematics. On the other side, we have the inferential approach that goes back to Gensen in terms of, first of all, his natural deduction calculi, and then his L calculi, LJ for intuitionistic logic, LK for classical logic, developed the natural deduction calculi, developed first rather systematically by Doug Prawitz, 1965. Other approaches to the inferential criteria are by Ian Hacking and a number of others. I think that we should be looking at a combination of these two in a certain way. And there's no question which propositional operations, we're going to be talking entirely about classical logic here, although I will bring up the question of intuitionistic logic at the end. So we know in full which are the propositional operations. They can all be reduced to a basic few, conjunction negation, for example. So the question comes down to quantifiers. And there is, I don't know if you would say the most general notion of quantifier, but at any rate, a rather extremely general notion of quantifier due to Per Lindström. And I'm going to ask which of those ought we to be considered as logical when we combine them with conditions on rules of inference for how we might use those quantifiers. And the inferential part of this criterion was first proposed by Jeffrey Zucker in 1978 in the Journal of Philosophical Logic. It's an article which has sadly been overlooked. I think it's quite interesting. And the idea is that the rules of inference, I'll show you examples, uniquely characterize the quantifiers or logical operations via their axioms and rules of inference. So my own view of how the meaning of a quantifier is to be specified is we simply accept that given by Lindström, and that's quite common, done in model theoretic logics and quantifiers in natural language in the excellent book by Stan Peters and Dag Westerståhl. Whereas Zucker thought that the meaning of a quantifier is specified by its axioms and rules, provided they uniquely determine it. An even weaker condition had been proposed by Gensen. So the criterion is that a quantifier in Lindström's sense is logical only if it is uniformly, uniquely characterized by some axioms and rules of inference over each universe of discourse. And the main result will be that a quantifier meets this criterion just in case it's definable in first-order logic. So logic is first-order logic if you accept this. So to describe the setup more precisely, going to be talking about various universes of discourse, non-empty set U and predicates on U considered as KR relations or as propositional functions into set consisting of truth and falsity. And depending on which way we're looking at it, we'll either say that the relation holds or that it's true. And a global quantifier of type K1 up to Kn, that is operating on predicates P1, Pn, Pi of Ki arguments, is simply, in Lindstrom's, according to Lindstrom's definition, a class of relational structures of that signature closed under isomorphism. So a typical member of that is a structure of the form U with P1 up to Pn, where U is non-empty and Pi is a Ki array relation on U. And given that, with each particular domain is associated a local quantifier, Q sub U on U, which is the relation which holds between the predicates of the appropriate number of arguments in the obvious way. Now, quantifiers can be given in set theoretical terms to meet Lindstrom's definition without restriction. In the sense of without mathematical restriction. So some simple common examples are the uncountability quantifier operating on unary predicates, which says simply that there are an uncountable number of elements which satisfy it. Equicardinality quantifier on two unary predicates, which say that they are of the elements which satisfy them are of the same quantifier. Are the quantifier, most P's are P1s are P2s, so that can be defined in cardinality terms. Now, even though the definitions of these refer to supposed totalities of relations of a certain sort, namely those needed to explain one-one correspondence and so on, and in terms of arbitrary subsets in order to talk about cardinality, actually, these quantifiers satisfy what I call the locality principle, that if the truth or falsity of Q sub U holding at P1 up to Pn depends only on U and P1 up to Pn, and not on any such totalities. Simply, does that combination U with P1 up to Pn belong to the quantifier, that is, the class of relational structures Q? Now, we can use this as a formula constructor given any first-order language with a specified vocabulary. We can enlarge it. We can add Q as a formal symbol to construct formulas. A new formula from given formulas psi1 of arguments x1. x1 is a sequence of k1 variables. Y is parameters, psi n, xn, kn variables, same y parameters. And we quantify x1, xn. So the xi's are supposed to be sequences of distinct variables of length k1 up to kn. And in order to define satisfaction, knowing how you have already defined satisfaction for the psi I, you look at the given any assignment B to the parameters of the psi I, and looking at which AI's satisfy psi I, that forms a predicate PI, set of KI tuples AI satisfying psi I. You look at those predicates P1 up to Pn on our domain and ask whether it belongs to the quantifier Q. If it does, that then is what makes the formula satisfy. Now, that's the semantical part. Let's go to the inferential part. As I say, this goes back to Gensen and his natural deduction and sequential or logical calculi. Gensen said something that seems a little surprising. He said the introduction rules for natural deduction represent, as it were, the definitions of the symbols concerned. Now, Prawitz explained this in terms of his inversion principle. You have a process of normalization that can be applied in the natural deduction calculus, in J, also in K. And so if you have a normal derivation of a conclusion with an introduction, then if you look back, just immediately back, you see that you have there the consequences of the elimination rule. So for example, if you infer conjunction A and B, a normal derivation of that, just above that you'll have derivation of A, you'll have derivation of B. So you can infer, in a sense, infer A and B separately from that. So that is one way of spelling out Genson's idea. But let's look at the introduction and elimination rules together and see in what sense they're implicitly complete. And that is that any other operation satisfying the same rules of introduction and elimination will be provably equivalent to it. And I'm going to set this up not in the natural deduction calculus, or you can read that, you could read them if you want in that way, but in the sequent calculus. So, and you may have, in the classical case, more side formulas, both in the antecedent and in the consequent. I'm only showing the side formulas that are actually needed. So the introduction rule in natural deduction for implication is simply right, is looked at as right implication, right rule for implication, and the elimination is the left rule. Okay, now if you have another operation implies prime satisfying the same rules, from the left rule for you can make a simple little argument to show that P implies Q proves P implies prime Q by taking P implies Q for R in the rule R implies prime. And very simple proof of that. And inversely, we get by the other substitution. Similarly, for universal quantification, here are the rules. And if we given an operation for all prime that satisfies the same rules, we can derive the equivalence of the two by appropriate substitution. Now, I'm going to consider a slightly modified form of these rules by shifting to a Hilbert-style formulation. The double arrow, by the way, is I'm using for rule of inference. So in place of the turnstile, as we have up over there, Hilbert takes implication as basic, so we can use it throughout. And so from R implies P of A, we may infer R implies for all x px. And for all x px implies P of A corresponds to those. So those, the super H there indicates that these are Hilbert-style formulations. Now I'm going to formulate in general what rules could look like in a second order you might call meta-language for inferences. And that's, so L2 has variables for individuals, it has variables for propositions and propositional functions. I'm accepting the operations of first order logic is already given, because we want to know what more ought we to accept as logical. But looking just back at the rules for universal quantification, we might translate that into a condition on that quantifier read this way, that for every predicate, unary predicate P, for every proposition R, if for every A, R implies P of A, then R implies the universal quantification applied to P, and for every A, if Q of P holds, then P of A holds. And put in that form within this language, you see that if you have A of Q and A of Q prime, then Q is equivalent to Q prime. So very quickly, the syntax of this second order language has individual variables, it has propositional variables, predicate variables for each superscript K. I'll drop the superscript when it's determined by context. We can form propositional terms by applying a propositional, a predicate K or a predicate variable to a sequence of individual variables. The atomic formulas are simply all propositional terms. They express, at the same time, not only are they terms, but they express what we consider truth or falsity. And we close the formulas under the operations of the first order predicate calculus. And semantically, for this meta language, the interpretation is that the individual variables range over a non-empty universe U. T and F are the range of the propositional variables representing truth and falsity. Predicate variables range over propositional functions of the right number of arguments. And they may, in accordance with the locality principle, they may be taken to range over any subset of the totality of K predicates over U. And satisfaction is defined in the standard way, starting with if you have a propositional variable and an assignment to it that it's true just in case it's true. Now we can extend this by a quantifier Q, and the language is extended in the obvious way, saying which are the propositional terms, which are the atomic formulas, and how satisfaction is to be determined. So, in general now, the criterion for logicality that I'm proposing is to look at a formula, a sentence A of Q in the language, the second order meta language, L2 of Q, a formal meta language, as was done above for the universal quantifier. And so coming back again to what I call the semantical inferential criterion, I want to emphasize here that it's a partial criterion. We'll come back to the issue of why it's not necessary and sufficient, but just only a necessary condition. That a quantifier Q is logical only if there's a sentence in L2 of Q such that for each model, Q sub U, the restriction of Q to the domain U is the unique solution of A of Q when restricted to the predicates of that model. Now, I spoke about a statement A of Q is completely characterizing a quantifier inferentially, but we have the ordinary notion of completeness of a language with a quantifier which might be defined in set theoretical terms. For example, Kiesler looked at the quantifier uncountably many and gave a complete system of axioms for that, but that completeness is different from the one we're interested in because there at least Aleph 1 satisfies his axioms, there at least Aleph alpha satisfies his axioms. Any one of those is a solution of A of Q in his case, but these are not equivalent. This is not uniquely determined. So the main theorem is that if logical quantifier Q satisfies the criterion, then it's equivalent to a quantifier defined in first order logic. Well, the obvious idea is to try to apply Bett's definability theorem. If you have A of Q and A of Q prime implies that Q equivalent to Q prime, then you show that Q is equivalent to a formula without Q. And that, in fact, was the basis of the proof that proof idea that Zucker had proposed in 1978. A bit of a different second-order language than the one here. The problem on the face of it is that Bett's theorem doesn't apply to second-order languages unless the semantics is considered in the Henkin sense rather than the full sense. It fails for full second-order logic. But because of the locality principle here, we can restrict the Henkin models. So one way to apply Bett's theorem here is to think of it as applying to second-order languages and Henkin semantics. I have a reason for instead simulating the second-order language in a first-order language, which you can always do with things which have a general semantics, and applying Bett's theorem there. But even then, as we'll see, we need something further to carry through the proof. For the first-order language, L1, very similar looking to L2. Everything is supposed to be at the first-order level here. So individual variables, this is many-sorted first-order. So we have individual variables, propositional constants TF, predicate variables of k arguments, and predicate constants, which represent the constant identically true. And we want to be able to apply predicate sorts to individual sorts to get objects of type T and F, propositional sorts in effect. So we have application operations to do that. And the terms are built up in the expected way. And atomic formulas are simply, if you have two propositions, you ask whether they're the same, that is, whether they're both true or both false. And it's useful to have a base set of axioms for this, which simply says T and F are distinct, that every proposition is either equal to T or F. The T sub K are identically true, and we have extensionality. And then semantics of that is defined in the obvious way. We're assuming we have a set which is the range of the k-array predicates, but since we're not talking about full second order, simulated at first order, this is simply some subset of the k-array predicates. And there's an obvious relationship between these two languages, the second order language and its simulated language, L1. With each formula of L2, we can translate that into a formula A down of L1. Simply replace each atomic formula alpha of A by a formula which says that it's true, that is, that it's alpha equals T. And there's a simple inverse translation. So to prove the main theorem, suppose we have a sentence A of Q, which is a unique solution in over each domain that Q sub U is the unique solution over each domain of A of Q. Then we have in L1 the equivalence of Q and Q prime. We apply Bett's theorem and for many sort of first order logic to get. But what that gives us is a formula of this language L1, which has, besides individual variables, variables ranging over propositions and variables ranging over predicates. So that's not a definition yet in first order logic. we have to get rid of the proposition and the predicate variables. We get rid of the proposition variables simply by replacing them by their instances, T or F. But now to get rid of the predicate variables, I consider a relation between two structures, U and U prime of L1, where U E prime, but we may have more predicates in M1 prime than we have in M1. And the formula B that we had by Bett's theorem, which sits in L1, still with predicate and propositional with predicate variables in it, is invariant. It holds in M1 if and only if it holds in M1 prime because of the locality principle, which says it doesn't matter how many predicates you have around. It just depends on the actual predicates P1 and P1 at which you're testing it. Now, that shows that that formula is invariant under what I called outer extensions in an article that I wrote in 1968. In that article, I proved that the formulas that are invariant under outer extensions are simply equivalent to formulas definable using only quantification over the stationary sorts, where the stationary sorts simply are the objects ranging over the domain U in this case. So that's a reduction to first order logic. A complete reduction to the first order logic. And well, there's a small technical point that we have to get rid of additional variables that may be sitting around. For those, we use the constants T super K. So Bett's theorem was not enough. You had to apply an additional argument to get rid of these additional propositional and predicate variables. Now, as I said, I consider this only a partial criterion for logicality, a necessary condition. What would be a necessary and sufficient conditions? Well, the point is that there are many mathematical notions that which may be considered as Lindstrom quantifiers, and when considered as Lindstrom quantifiers, are definable in first order logic, but we would not ordinarily consider them as logical. For example, what does it mean to be a group? Thinking of a group as something on a domain U given by a three-place relation for the multiplication relation. We can explain the conditions for that in first order logic using also equality. I mentioned this point here because there's controversy in literature on the philosophy of logic, whether equality should be considered a logical notion. Is it a logical notion or a mathematical notion, right? So if you're worried about this, replace talking about groups by structures UPE, where E is a congruence relation on the relation P. That's still a mathematical notion that we would not consider to be a logical notion. So not everything definable, not every quantifier definable in first order logic ought to be called logical, according to this criterion. Right? That's why this is only a necessary condition for logicality. So to tighten this to a necessary and sufficient condition, we need to tighten just how we're describing the axioms and rules of inference for a quantifier Q. And so for that, we would like to have a much narrower explanation of, well, just what is in natural deduction calculi or sequent calculi the most general form of axioms and rules of inference. That was considered by Zucker, also in a related paper by Zucker and Tregesser. The answer should come out the same, of course, that, but Exactly how that's to be done is not clear. So the moral of all this work so far is simply this. If you accept the setup that I was describing here, if you take semantics given by Lindstrom quantifiers and you accept this criterion, which is the partial criterion, forget about whether you can get a nice necessary and sufficient condition, you don't go beyond first order logic. Logic is first order logic. Now, just a couple of more points here. All this can be extended to countable admissible, logic on countable admissible sets. This is just a kind of a technical question. Besides our quantifiers there, it'd be interesting to consider propositional operations. That's not a question that arises in the finitary case. Are there possibly new propositional operations that satisfy the criterion? But more interesting is whether there are analogous results for intuitionistic logic. Well, here it's not so clear which semantics we're talking about. So there have been various proposed semantics in the literature. One, what's called the BHK, Brouwer, Heiting, Kolmogorov semantics, which takes the notion of construction or constructive proof, or both, as a primitive. There's the Kleene version of realizability, generalized in various senses. There's what's called inferential semantics, simply what's given in natural deduction, NJ, natural deduction intuitionistic calculus, generalized in some way by using inferences. That's, well, I'll come back to that in a moment. Or there's forcing in Kripke structures and maybe other kinds of semantics that we're talking about. So if you look at inferential semantics, this is something that was treated by Zucker and Tregesser, and they show that, again, you don't go beyond intuitionistic logic in that case. What about forcing in Kripke structures? Well, every quantifier in Lindström sense can be carried over to Kripke structures in general in a fairly obvious way, so that the notion of forcing has its usual properties over Kripke structures. But you're not going to get anything new there, because if you consider Kripke structures with just one world, you're back in classical logic. So since we know if we applied our thing to arbitrary criterion to arbitrary Kripke structures, then it applies fortiori to one world Kripke structures, and therefore you get from the result that we had here, everything is definable in first order logic. I don't consider any of this very satisfactory, but it would be nice to see whether there's some precise sense in which one or two can be considered. Here are some references. So the 68 paper that I was talking about, which was essential for the proof, 2010 critique of the invariance criteria, Gensen and Lindström, Peters, Westerstall, and the two articles of Zucker and Tregesser, which were the real background for what I was doing here. Thanks so much.
Okay, questions?
When you assume that the formula defines implicitly a quantifier like in Zucker's paper, do you assume that the quantifier is an instant quantifier?
Yes, it is.
So you express that in the second order.
We're assuming every quantifier that we're dealing with here is a Lindstrom quantifier, and the question is whether on each domain U, Q sub U, Q restricted to U, is the unique solution of that A of Q.
As far as I remember, so there's quantifiers which are not Lindstrom. But when you define the second order language, can you express in that language the property of the quantifier of being closed under isomorphisms?
Of being what?
Closed under isomorphisms.
The quantifier itself, no, we don't express in the second order language that it's
But you
closed.
see, if you assume, if you restrict the Lindstrom quantifiers, you get more implicit definitions. Because there may be like, because there are these two concepts of quantifier, there's the Lindstrom quantifier and then the more general where you don't assume that it's closed under definition. And it's clear how you express the second one, but if you assume that they are Lindstrom quantifiers, you have to also say that it's closed under isomorphism, and I don't see how you say that in the...
No, you can't say that in the second order language. There's no reason.
Okay, well, of course the result still makes sense, but since you started by saying that you assume the Lindstrom quantifier and then the implicit definer, and then syntactic definability, then you could also combine them right away and you would get more quantifiers. And
Yes.
then it's not clear whether they are Lindstrom.
So I think your point is we never use the condition on Lindstrom quantifiers that they're closed under isomorphism.
Yeah.
Right.
Okay, so, okay, I have another question.
Yes.
The Siberian Fund for Algebra Logic has a journal called Algebra Logiki, and I suppose it puts algebra first because of alphabetical order. But my question would be, what rests on what? Do you see algebra as resting on logic or vice versa?
Excuse me, Ron.
Sorry. Right. So I was talking about the journal Algebra Logiki, if I remember. Sorry. Yeah. Okay. Right. Did I pronounce it right? Sorry.
Close enough. I'll get rid of logic practice.
Oh, thank you. Yes. Logic. Yes, I only got that bit wrong. My question to you is, what do you see as resting on what? Do you see algebra resting on logic or vice versa?
Do I see algebra as resting on logic or vice versa? Hey, that's an interesting question.
It's a great question for Pascal and Watson. One, we know how useful.
I see logic as basic to all reasoning.
Well, you see, the reason I asked the question was that Phil made a comment to me. He said, "Oh, that's just an adjunction." And I thought, gosh, actually, Phil is right. And so you can take everything he said here and rephrase it in a foreign language, the foreign language being kind of category theory, which is spoken by Australians and Canadians and other foreigners, and it will all come out with the same results, maybe a little different in some cases. The concept of type might be slightly different when you have multi-sorted algebras, but basically you'd be saying the same thing again. So it would just be interesting to see the same material presented in this other language, to go back and forth and say, do we learn anything different from the two languages, or have we just learned the same thing in either case?
Well, you're welcome to.
Arnold?
I have reservations, two political reservations about your criterion of uniqueness. First, it seems to me that you actually using the word something stronger. You only prove that A follows from B and B follows from A, so this is uniqueness. But in fact, what you are doing is congruent, so you can substitute A for B everywhere. If I understand correctly from the semantic, this is usually what is uniqueness, that whenever you write A, you can write B instead and get and preserve inferences. Okay. So not only, it's also in the context. And this is not usually part of the definition of a logic, this condition of the substitution of equivalence. So being equivalence is not really unique. It doesn't really mean being unique. That's one reservation.
So we started with an observation that the usual operations are good for familiar. are uniquely determined.
No, you say I said that A implies B and A prime, and A prime B follows for each other.
Yes.
But that doesn't mean, for example, the negation of this follows from that without further assumption about negation, for example. So in most many value logic, you don't have substitution of equivalence. In most many value logic. So it seems to me you assume here that the logic should have the property that if two sentences follows from each other, then they can be substituted in every context.
Substituted in every context. That's an additional condition that we might impose, yes.
So it doesn't follow from the semantical in the characterization.
It's an additional condition we might impose, but without imposing it, we wouldn't see it.
That's what I mean. So, but really, you think if you impose something stronger, then what are you going to say?
Let me answer this. We try to say just what is logic. There's a lot to think about. We put it in very narrow terms here. And we said, even if you put it in these very narrow terms, you don't go beyond first order logic. So it seems to me it's a very strong result by saying we're not imposing much on the criterion as to what is a logical, what is a logical concept. We're just, maybe we should discuss this.
So the other side of the coin is that to which are independently from many studies another deterministic connected with quantifiers. So there is certainly no problem with this. And this goes back also by the way to shoot Girard, some kind of semantics of the capital.
I'm not sure what the issue is, and I think we better discuss this in further.
Just one last one. Hein, you had your...
Well, it's a long question.
How long is the answer?
Okay, let me just do it. I mean, you answered, I want to follow up you answered logic is a general theory of reasoning, pure reasoning, or something like this. Right. But you assumed a very particular set in which to investigate it. I mean, there is a certain tension between it. For example, you assume that you have predicate logic and the task is semantics and the model is the structures and so on. And the question is whether you have thought of ways of adding additional criterion so that you can extend it to further sets. But for example, I propose to do the following thought, that since it's a general theory of reason, it is imperative that the set of purely logical theorems should be computable. I agree. So, and this can be applied across the board. This might rule out certain infinitary logic, which here sometimes I don't know.
It just doesn't go there.
That's true. That's true.
I mean, back in the days when we were doing model theoretic logics, and you had the question, if you have a logic where the validities are recursively enumerable and you have interpolation theorem, but is there anything beyond first order logic? And Keith Schiller came up with some wild logic that requires some extraordinary
that's true.
high infinity. So I don't know. I mean, those of course were always interesting directions to pursue. But every result is in a certain setting. You say I have this in a certain setting. Everything we talk about here is in a certain setting. This seemed to me a fairly general setting in which to raise the question.
Okay, I think we're going to have to move on now. Thank you very much.